Assalamualaikum warahmatullahi wabarakatuh. Can you guys hear me? Assalamualaikum warahmatullahi wabarakatuh.
Salam.
Good. I seem to be not having a good reception. There's only one person that respond. I'm not sure what's happening to the rest of you guys. Anyway, I'm not going to show my video. I'm hoping that will help with the WebEx so that we will not have any lagging. Is it lagging on your part now?
No.
Is it lagging? No, good. Well, somehow you guys doesn't want to respond verbally. You guys want to respond using the chat. No problem. Okay, that's good. I have the QR code now on display. So let's see how many participants are there actually now. Okay, 25 of you guys, but somehow the attendance only recorded 24. Somebody hasn't scanned? Okay, good. That's 25. Okay, let's talk about your test 2 first. Before we start, we continue with an example. You will have your second test on the 23rd of December. That's on Wednesday, this coming Wednesday. Again, it will be conducted at night. You will have it at night. Okay, and it will be from 8 p.m. till 10 p.m. You have only 2 hours to complete 3 questions. The 2 questions, 2 of it will be on single phase. That means there's no change of phase. The second question will be on multiple phase, meaning there will be a change of phase. It's from liquid to vapor or vice versa, or from solid to liquid or to liquid to vapor. And the other question will be on psychometric chart. You need to submit the chart itself. The question required you to submit the chart itself. So you need to print the chart. Okay, you need to print the chart. The chart will be given to you either a day before the test or on the day itself. So you need to print it up and do your working on that chart and submit it together with the answers. So again, as usual, you need to scan your solution, and then you need to upload it in e-learning. Okay, so you're only given 15 minutes to do that. So if you delay, you will not be able to submit in e-learning. And I prefer not to accept it using WhatsApp because I need to download all of you guys together in one folder. Okay, so when you upload it in e-learning, so it will easier for me, or else I have problem getting from WhatsApp and then transfer it to that folder. And another thing that I need to remind you guys, please scan your solution. Make sure that your scan is very sharp. Based on last test, there's some scan that based on the quiz. Some of your scan is not that sharp. Okay. Somebody just left. Ikram just left. Okay. We haven't started anything yet. Somebody already left. Okay. What else that I need to mention? 3 tests, 3 questions. Sorry, 3 questions in 2 hours is not. It's really just enough time if you know the stuff. If you know the stuff, it will not be that difficult. Okay, thank you, Ikram. Yeah, okay. You have to, okay. Okay, Ikram. So you need to really know the stuff. You cannot waste time flipping from one page to another page trying to find a similar example. You need to know it. You need to really know how to solve it. But if you want to check After you have, if you want to double check, no problem. But I don't think you have any much time to spend looking up the internet to see anything that looks similar to it. You don't really have that much time. So you have 3 questions, 2 hours. You can just divide it roughly, maybe 45 minutes each question. Okay, 45 minutes each question. And then you have ample time to double check. If it's 45 minutes, that's about 1 hour and a half. Is it? For 3 questions. Anyway, all the very best to you guys. Today we're going to start with, we're going to continue with what we were doing. We were looking at the psychometric chart. So you really need to know about the psychometric chart, how to use it, how to read it, how to get the values from that chart. We have done a few examples before this, so we will continue with another topic, which is adiabatic cooling. So I'm going to stop sharing this QR code for those that haven't, that's come in later, and later then we will share it again towards the end of the lecture. So I'm going to share my iPad as usual. Okay. Okay, now I did introduce a bit about this adiabatic cooling. As the name implies, adiabatic means that it is Q is equals to 0. Or your heat is not being transferred or being absorbed from the surrounding. It's just between the system itself, within the system. There's no heat in or heat out into the surrounding area. It's just within the system itself. That's what adiabatic is all about. So what happened over here is that you have hot air coming in, and you spray liquid water into that hot air. So what happened is that water droplet will evaporate into your air. So there will be evaporation going on from the water droplets. And when the liquid water evaporates, it absorbs heat from the hot air. So what happened? The hot air will cool down because its heat has been transferred to the liquid water. So there is heat coming, the heat, sorry, let me undo that. The heat is being taken from the hot air, going into the liquid droplet, which cause the liquid droplet to evaporate. This is the system that sometimes you see in an outdoor restaurant at the patio, where you can see a huge fan with mist or water droplets being sprayed into the fan, into the front area of the fan. This is the same principle, whereby the water droplet evaporates, causing the surrounding air to cool down. This is what is happening. Sometimes you also have the portable aircon. It's not really an aircon, but it's a portable aircon that use the same principle, which has the mist, which is going to be sprayed in front of the fan. Yeah. So this is the same principle. Well, when you look at it from the psychometric chart, if this is your initial temperature or point of interest on the psychometric chart, at the initial temperature, the initial temperature is T1. Okay. When you do the adiabatic cooling, your temperature will drop to T2. Your movement from T1 to T2 is along the enthalpy slanting line. It's along that enthalpy slanting line, or the wet bulb line. You'll be moving diagonally along that enthalpy line. So if you proceed to further towards the enthalpy scale, your enthalpy will be the same for both the initial and the final position, or initial condition and the final condition of your A. So the enthalpy is the same. It doesn't change. Okay. The only thing that change is there's two things that changes over the two things that change over here is your temperature. That's obvious. The air is being cooled down. The other thing, the other parameter that changes is your absolute humidity. From the humidity of the air now increases. It increases from, let me write that down, HA1 to HA2. The absolute humidity increases from the initial position to the final position, because water vapor evaporates into your hot air, so there will be more water vapor in your air. So that's why the humidity increases. The absolute humidity increases. So there's two things that you need to take note of. There's the decrease in the temperature and the increase in the absolute humidity. So that is all about cooling, adiabatic cooling. You cool down the air adiabatically. Yeah, so that's what you need to know about the humidity chart. Yeah, I'm not going to, I have already introduced this part. So let's see whether, okay, there's another thing that you need to find sometime. The adiabatic saturation temperature. Adiabatic saturation temperature. The symbol is capital T subscript AS. This is the same principle, except that now, if you look at this diagram, your liquid water is not in a droplet form. It's really huge. You have a very long channel here, a very long channel containing liquid water. Your hot air is coming in at I need to write that at T1. Yeah? Having an absolute humidity of HA1 and the relative humidity of HR1. Right? So by the time the water evaporates into that air, the inlet air, because of the very long distance that the air have to travel over the liquid water, by the time it reach the outlet, that air at a temperature of T2 will be saturated. That means your relative humidity is going to be 100%. Before this, your relative humidity is less than 100%. Yeah, if it's 100%, there's no way it can accept any more water or vapor. So by the time it reaches the outlet, it should be saturated. And your absolute humidity is going to be denoted by HA2. That is your absolute humidity. Definitely, your absolute humidity is much, much, much greater than HA1. Okay, the inlet, the value of the inlet. So this is the temperature. T2 is going to be your adiabatic saturation temperature. That is your adiabatic saturation temperature. That's the title of the slide, your adiabatic saturation temperature. So how to find that adiabatic saturation temperature is by going towards the 100% curve. This is your 100%. That's your 100%. So in order to find the adiabatic saturation temperature, it will be on the 100% curve. It should be on this curve, 100% curve. Okay. So if you project it until it reaches that curve, then you will get your adiabatic saturation temperature. That's the equation here. Let's look at this. Okay. This, oh dear, what am I doing? I'm trying to highlight this. Your adiabatic saturation temperature is the same as your T wet. Why? Because your T wet is also obtained on the 100% curve. So if you drop that down here, you will get your T wet or your adiabatic saturation temperature. It will be the same. Okay, your adiabatic saturation temperature is going to be the same as your T wet bulb temperature. And if you want to calculate it, for example, if you wanted this to be if you wanted to calculate the temperature of your outlet, this is the equation that you can use. This is the equation that you can use, provided you know the latent heat of your water at T2, at the temperature of the outlet temperature. You need to know the latent heat of your water at the outlet temperature. If you know that, then it shouldn't be a problem to calculate the outlet temperature. But if you're going to use the if you're going to calculate the adiabatic saturation curve, the adiabatic saturation temperature, you can just read it off from the psychometric chart by projecting your line from the point of interest, the initial condition, to the 100% saturation curve. And then you drop it, you will get your adiabatic saturation temperature. It's going to be the same as your T-wet temperature. T-wet bulb temperature is going to be the same as your adiabatic saturation temperature. That's another thing that you need to know. Okay, let's see whether we have one example. Okay, over here we have one example. Any questions so far before I proceed with the example? Anybody want to ask anything on this topic? Anybody? Clear. Good. Thank you, Ibrahim. Somehow nobody want to speak. Everybody prefer writing. That's a bit okay. No problem. But it took quite some time to type. It's faster to speak, but then it's no problem. Okay, so let's proceed with an example. This is one example in your textbook. You have, let's read through this question. You have a stream of air at 30 degrees C, 10% relative humidity. It's going to be humidified in an adiabatic spray tower. The pressure for that system is 1 atm. Your air is going to have a relative, the outlet air is going to be set, it's not going to be saturated, it's going to have a relative humidity of 40%. You need to find the absolute humidity. You need to find the adiabatic saturation temperature of the entering air. Okay? That means you're going to find the T-wet. The adiabatic saturation temperature and the T-wet is going to be the same. So let's look at our, I don't have my chart over here. I need to get my chart. I need to use the psychometric chart. So let's look at our psychometric chart in SI unit. Let me erase this. So there's too many things over here that will get us confused. Tidy it up. Okay, let me bring this over to that example so that we can have everything in the same slide, the same view. I mean the same slide. Let me just copy this. Remember, you need to print your, you need to print the psychometric chart. You're going to have the same psychometric chart given to you. So let me copy this first. Okay, now let's go back to that example. You need to submit your psychometric chart for the question on psychometry. You need to submit it. Do not forget to submit it. Yeah. Okay, that's done. Let's see what is being asked here. You need to locate your first inlet, your inlet air position on the psychometric chart. The air is at 30 degrees C and 10 relative humidity. So let's look at your psychometric chart. I'm going to change the color of this pen so that it's not going to be black, or else it's going to be it will not be that obvious on the psychometric chart. So let's use red. It's at 30 degrees C. That's 30 degrees C. I'm going to project a straight line. Try to get a straight line. Yeah, that's a straight line. And the relative humidity is 10 degrees C. So if we highlight the 10 degrees C curve, that is the 10%, not 10 degrees C. That's the 10% relative humidity curve. So where the where the two of them intersect, which is the 10% and the 30 degrees C, is the point of interest. So if I enlarge this, our point of interest is going to be here. So that is your inlet position of your air. And what else do we need to know? What else do we need to find? from this question, you are asked to determine the absolute humidity. So the absolute humidity is the one on the right hand side, which is on the y-axis. Your absolute humidity is the moisture content. So if you project it horizontally from that point of interest to your, oops, I did not do that. Therefore, from that point of interest to the y-axis, you going to get a straight line. Okay. Roughly, if you look at the scale, it's going to be 0.00224 about 5. If I enlarge this. Okay, about 0.00260025. That's roughly the value of your absolute humidity. So let's have a look at the solution. Okay, the solution here gives you a value of 0.026. That's what I did. What's roughly what we also obtained just now when we were looking at the psychometric chart. It depends on how straight your line is, and also how you draw your line actually. Okay, so it's roughly about 0.0026. The other part of the question asks for the adiabatic saturation temperature. So in order to get the adiabatic saturation temperature, you need, okay, I'm going to change the color to green. You need to project from your inlet condition diagonally towards the enthalpy using the enthalpy line. So your enthalpy line, this is your enthalpy line, right? That's your enthalpy line, the diagonal slanting line. So you project from your point of interest to that, to parallel to that enthalpy line towards the 100% relative humidity. So I'm going to draw that line, a straight line diagonally from the point of interest towards the 100%, parallel to the slanting line. Make sure I can get it straight. Okay, that's roughly a straight line. So if you look at the 100% curve, you also have the temperature given there. The temperature, this is 10, that's 15. Let me undo that. I'm not going to have it in green color. Let me use the red color. Okay, that's 10, that's 15. So our adiabatic saturation temperature is about, let's see, 11, 12, 13, about 13.5. Roughly, that could be 13, could be 13.5, but I don't think it's 13 because it's not directly on the enthalpy line or the wet bulb line. It's somewhere 13.4, 13.5 roughly. So let's have a look at the solution. (13.2). Okay, this is the answer over here. Give you a value of 13.2. Now I said our value is about 13.5. So that's acceptable. The answer 13.2 is not an absolute value. The author also obtained it using the psychometric chart. So it's acceptable, 13.5, 13.2. But definitely it's not going to be 13 because 13 is here. If you look at 13, that's 13. So it's not on that line, on the slanting line at 13 degrees C. It's not definitely not 13 degrees C. Okay, so that's how you get your adiabatic saturation temperature for that inlet air condition, Okay, next, what's the question asked for? Calculate the rate of water that must be added if you're going to have 1,000 kilogram per hour of the entering air and the temperature of the exit air. Okay, we know that the air is going to come out at 40, let me circle this, at 40% relative humidity. We know that. Okay, so we're going to highlight that 40% first on the chart. So if I'm going to highlight the 40%, so this is the 40%. Okay, that's the 40%. From the intersection of your line, the red line, the diagonal line, the red line that is going diagonally towards the 100% relative humidity, from that intersection of that red line with the 40% relative humidity, you will be able to get the point of intersection, which is over there, okay? Which I just was, that is your point of intersection. Let me undo that. This is your point of intersection. So if you look at that point and drop off the get a straight line going towards the x-axis. I'm not really doing it very well because it's not really a straight line. Yeah, I'm not making it. Okay, it's not really a straight line. It will be roughly 21.3 maybe. It's not really a straight line because I can see that it's not a straight line. It's about 21.3. That's the temperature of your exit temperature. So let me write that using a black color ink. That's about 20. Okay. 21.3 maybe. We see roughly. So let's have a look at the solution. Okay. The solution over here listed it as 21.2. Well, very close. We got 21.3. Okay, we got 21.3, but the solution gives us a value of 21.2. If you get 21.2, if you get 21.4, obviously it's not 21 because it's not on that straight line. There is somewhere beyond 21. That's the exit temperature. The second part to that question, you need to calculate the rate of the water that need to be added in. That means the amount of liquid water that you're going to add into your inlet air. How are we going to do this? We're going to do a material balance on the air. Because we should be able to calculate that if we know the relative humidity of the inlet and outlet air. So let's get the relative absolute humidity of your air for the outlet first. Okay. So your outlet temperature, we already managed to get just now. Now we need to get the absolute humidity. So from the point of interest of the outlet condition, that's the I'm going to use black now. No, I better not use black. I'm going to still use stick with red. So that's the point of interest. I'm going to project a straight line. Oh God, this is really not a straight line. That roughly there. And that is your absolute humidity for the outlet condition. It's about 0.006. Let's see. I would say it's not 3 because my line is not really that straight. If you have a look at the line, not really straight, it's about 0.0062. Okay, so let's take it as 0.0062. That's for the absolute humidity of the outlet A. So I'm going to write that here. My outlet A is going to be here. So I'm going to write that in black color in HA2 is equal to 0.0062 kilogram. I don't have enough space to write. Kilogram water vapor per kilogram dry air. And the inlet just now, for the inlet A, we managed to get about 0.00, let's use 0.026. Okay, for the inlet A, we have the absolute humidity 0.0026 kilogram water vapor per kilogram dry air. Yeah. So the amount of water that we're going to add in, we're going to give it a symbol of M with a dot. That's a flow rate. Kilogram water liquid is what's the unit per hour? Yeah, per hour. The question states that you're going to have 1,000 kilogram per hour of the entering air. So your entering air is going to be 1,000 kilogram per hour. That is your humid air. Why is it humid? Because you have 10% relative humidity there. It's 10%. Your relative humidity is 10%. That implies there is water vapor there inside your inlet air. So it's humid air. It's not dry air. It's humid air. But the thing is, in order to do the material balance for water, the unit for the absolute humidity is per kilogram of dry air. So you need to find the kilogram of dry air that is entering. The amount of dry air that is entering is going to be the same amount that is going to be in the outlet air. The same amount is going to be the same. I mean, it's going to be in the inlet and the outlet. So we need to find the kilogram of dry air coming in. And in order to do that, you need to get the let's see, you need to use the absolute humidity of your inlet condition. So let me write that using black ink. Alright. So coming in is 1000 kilogram per hour of your humid air, and you have a value of 0.0. I need to find the kilogram of, let me see, I need to find the value of the entered dry air. Anybody have any idea? I can find the value of the dry. I can find the value of the water if I use the humid absolute humidity, but not the value for the kilogram of dry air. So anybody have any idea how to find it? Anybody? Nobody? Okay, let's undo this first. What did I say just now? You have a 1000 kilogram of humid air. Humid air. Humid air contains water vapor plus, let's get a picture of it, plus dry air. This is what we want to find, the kilogram of dry air. What's the amount of water vapor? We know we have the absolute humidity. So let's say, let there be 1 kilogram. Just let's assume that there is 1 kilogram of dry air. Based on the absolute humidity of the inlet air, you have a value of 0.026 kilogram water vapor per kilogram of dry air. That is the value that you get from the psychrometric chart earlier, which is that value. If I enlarge it, I zoom in, that's the value we got, 0.0026 at that location. Okay, so that is the absolute humidity. So the unit is per kilogram dry air. So if you assume it's going to be 1 kilogram, if you're going to assume it's going to be 1 kilogram of dry air, so that means for every 1 kilogram of dry air, you're going to have 0.0026 kilogram of water vapor. Okay? For every 1 kilogram of dry air, you're going to have the amount of water vapor is going to be 0.0026. So the amount of humid air, so if we put that value over here, okay, your amount of dry air, we say is going to be 1 kilogram. And the amount of, let me put undo that. I'm going to use a red ink because I want to use red ink. About that's 1 kilogram. And the amount of water that you're going to have is about 0.0026 kilogram of water vapor. So the total amount of your humid air, don't look at this part. We're not going to look at this part because we already assumed that you're going to have 1 kilogram of dry air. So the amount of total humid air you're going to have is going to be, your humid air is going to be 1 kilogram dry air plus 0.0026 kilogram of water vapor. So that will give you 1.0026 kilogram of humid air. So we need to know this, because based on that value, then you can use it to change that 1 kilogram into dry air. Okay, because this is humid air. This is also humid air. Then you can change your humid air into dry air, the value for the dry air. So let's do that. Okay. Any questions so far? This is the tricky part. The part whereby you're going to use the information by assuming 1 kilogram of dry air. That's the tricky part. Any question? Anybody? Nobody? No question? Are you with me, guys? Am I speaking alone? I hope
Yes,
you're always
Doctor.
with me. Yeah, I hope there's no lagging, because I don't know what's coming up for your psychometric chart. Dr. Jamaliza is going to set that question. She only said that you need to print the psychometric chart. It's going to be given to you, the psychometric chart, and you need to print it out. And you need to turn it in together with your solution. You need to scan it together with your solution, because she'll be giving marks on how you get the values from the psychometric chart. So you really need to know that. And then this question, example 847, I'm not sure whether it's coming similar to this example or it's somewhere similar to the other example. I'm not sure. I don't know. So just be prepared. Okay. So let's. Any question before I proceed with the solution? Any questions? Because this is very critical. You need to know how to get the dry air value from the humid air value. Before this, we are given the volumetric flow rate of the entering air. We use the volumetric of the humid volume from the chart, but this is slightly different. You are given in kilogram, not the volumetric flow rate. Okay. Before this, we have been given, for the previous example that we have looked at, we are given the volumetric flow rate of the humid air, and you can get the convert it into dry air, the value of dry air, by looking at the humid volume from your psychometric chart. You have done that using the previous example. So the difference between this example is that your entering air is not given in the volumetric flow rate. It's in terms of mass flow rate. That's the difference. Okay. So now, to get the dry air coming in, I'm going to proceed further down here. You have 1,000 kilogram per hour of humid air, and you know that for every 1 kilogram of dry air, you have 1 point, this value, you have that value 1.0026, 1.0026 kilogram of humid air per kilogram of dry air, for every 1 kilogram of dry air. That's why when you did the calculation just now, you assume 1 kilogram of dry air, to make sure that this unit is for every kilogram of dry air. Okay, so now, using that value, you should be able to cancel your kilogram of humid air. You will end up with the kilogram of dry air every per hour. So if you do that calculation, your answer will be 997. Somebody check. I get that value from the textbook. Not sure whether that's the correct value. So let's do the calculation. Okay, 997.406. Okay, just right, 997.4. Okay, Sam, thank you, Muhammad Salim. Okay. Sam, Ibrahim. Okay, good. So that is your amount of kilogram of dry air coming in every hour. So if you look at the diagram, we're going to write that. I'm going to erase this. I'm going to write that the kilogram of dry air. That's dry air. That value is going to be 997.4. That's the same value coming out. 997.4 kilogram per hour of dry air. Same value coming out. Okay. So what is required now? We can proceed to calculate our rate of water coming in. Just now we use this symbol. We use M for the rate of water coming in. Okay. So we're going to do our energy balance. Ignore this three. We're going to assume that the amount of water coming in is the same amount that is going to evaporate. So there will be no leftover water coming out from the system. So we're going to do our material balance. It's going to be the air coming in the water coming in, that's one. And then there's the air coming in, that's the air coming in. That's equal to the air going out. But we're not doing our meter balance on air. We're going to do our meter balance on water. So let's do that. Water balance. Okay, so if you look at the diagram just now, you have two streams coming in, and one stream coming out. Right? So let's do our meter balance on water. The mass flow rate of the water that will be supplied into your adiabatic cooling tower, that's kilogram. I'm not going to write the unit. We know it's going to be in kilogram water. So because it's just on a water balance, plus the amount of water in the inlet stream. So you know that your amount of water in the inlet stream based on the amount of dry air and the amount of your absolute humidity. You can calculate your amount of water because you can cancel off your dry air. Okay, so let's do that. 997.4. Over here, I'm going to show you the unit. That's kilogram per hour of dry air. And you have the absolute humidity just now. We have 0.0026. Oh dear, it should not be at the denominator. It should be at the numerator. 0.0026 kilogram of water vapor per kilogram of dry air. That is your absolute humidity. So you cancel off your kilogram of dry air. You end up with the amount of kilogram of water per hour. So I'm going to erase this because I think I better put down the unit. I'm going to put down the unit to be consistent. Kilogram water, this is liquid per hour. So that's your inlet. Now your outlet, so if we look at the diagram again, the air going out still has the same amount of dry air coming out, but the absolute humidity is different. Now it's 0.0062. If you look at the stream going out of the tower, it's 0.062 kilogram water vapor per kilogram of dry air. So you're going to have the same value of the dry air, multiply it with the absolute humidity of the outlet air. That's per hour. And just now we said the absolute humidity, if I can just look at this diagram, it's going to be 0.062 kilogram of water vapor per kilogram of dry air. Cancel off the kilogram of dry air, you end up with all the terms, all of the term will be in terms of kilogram per hour of water, whether it's liquid or whether it's vapor. It will be your water balance. So now, all you have to do is solve for your amount of water that is coming in, or the rate of the water that have to be supplied is going to be, if you bring this over to the other side, it will be deducted from the initial, from the other term. So take out the same amount of kilogram of dry air, it's going to be the same. Right? So 0.0062 minus 0.0026. You will get a value of 3.7. Let's do the calculation. The answer from the textbook is 3.7. So let's do the calculation just to double check. Okay, 3.59064 kilogram per hour of water that need to be supplied. Well, that's slightly different from the solution of, given in the textbook. The textbook gave a value of 3.7. We managed to get 3.6. Slightly different, but that doesn't mean it's wrong. Yeah. I'm surprised that now I know why the solution is different. Because the textbook has a value of 0.063 there. We have 0.062. That's the slight difference. Okay. So that's your final value, your solution for the amount of the rate of water that need to be, or the rate of water that need to be supplied to your cooling tower or your adiabatic spray tower. So the question asks for the rate of water that need to be added. to humidify your 1000 kilogram per hour of entering air. So guys, any questions before we take a 5-minute break? Any questions? The most important thing that you need to take note of is again this part on the absolute how to get the amount of kilogram of humid air. You really need to know how to do that because it's not given in volumetric flow rate. It's given in kilogram of humid air coming in. So you need to assume 1 kilogram of dry air, and from the absolute humidity of your inlet condition, you should be able to get the total amount of your humid air. Let me write that down. The total amount of humid air is 1 kilogram dry air plus 0.0026 kilogram of water. So that will give you a total of 1.0026 kilogram humid air. That information will help you to solve the amount of dry air in your inlet stream and in your outlet stream for every 1 kilogram of dry air. Any questions? Okay, somebody asked a question. What? You got 3.59. 3.59. Arif, you got 3.59. Okay, same with me. I got 3.59. Thank you. Okay, there's another question from Hai Chin. Hai Chin, is it correct? Doctor, why is the output of liquid stream water is cancelled? Okay. Why is it cancelled? Because we're going to assume that the amount of air, the amount of water, the amount of liquid water coming in is just enough for you to evaporate in order to cool it down to the required temperature. The final temperature, which is the 21.2 degrees C, that's the final temperature and the final relative humidity. That's the amount of liquid water that needs to be evaporated or that need to be supplied to the inlet air in order to reach that desired outlet condition. So that's why we ignore the outlet water. Yeah, because the outlet water has nothing to do with cooling it down anymore. It's the excess water. You don't need it anymore. You just need the amount that will cool down your inlet air to the desired humidity and desired temperature. That's why you ignore the bottom flow rate of your liquid water. Okay, that's the reason. Any other questions? You guys prefer to type your question? No problem. Any other questions? Anybody? No questions? Okay. In that case, we take a break. Be back again at 10 past 9. I give you 7 minutes. Just round it off to 10 past 9. Okay, guys, let's take a break. We will look at one more example for today.
Doctor, can you show us the attendance?
Sorry?
Attendance.
Attendance. Okay, I'll show you the attendance. Let me unshare this first. Yeah, welcome back. We're going to do one more example. This is more like calling what we have done before in how to use a psychometric chart, and how to calculate the rate of heat transfer if you have an air cooler. But this example is slightly different because of the unit. Unfortunately, the unit given is in English unit. So okay, can you see the example? This is from the old textbook. I'm not sure in your new edition it's the same, but this is an old edition. The example state that you have an air at a temperature of 80 degrees Fahrenheit and a relative humidity of 80%. That air is going to be cooled down to 51 degrees Fahrenheit at the same temperature of 1 atm. So your process is done at 1 atm. Use the psychometric chart to calculate the fraction of the water that condenses. Remember, condensation only occur when you reach the 100% humidity, relative humidity. When it reach the 100%, that's when it start to have a single drop condensing. If you further cool it down beyond that temperature, then you have more water condensing. So this is what the question is all about. So the rate at which the water that need to be removed in order to deliver 1,000 feet cubic per minute of humid air at the final condition. So I have the diagram there shown. This is the diagram. You have a basis of 1 kilogram or 1 pound mass of dry air. Okay, just now when we did that example, just now the previous example, we need to write the basis. I forgot to write down the basis. So you need to write down the basis. For that previous example just now, what is the basis, guys? For the previous example, what basis should we be using?
1,000 kilograms.
Yes, per hour of the inlet air. Good. I forgot about that. So don't forget. Please remind yourself during the test the basis and the reference conditions or the reference state. You need that. Okay, I keep on forgetting about it. Okay, now for this example, you are not given the amount of the flow rate coming in, but you are given the volumetric flow rate of the air going out. Okay, if you look at my pointer, I'm pointing at the 1,000 feet cubic per minute of humid air at the outlet condition. But we are not going to assume that as your basis. We're going to assume 1 kilogram dry air because it will be easier that way. When you have done it, when you have just calculated it using 1 kilogram of dry air, you can scale it up to the final value of the dry air in your humid air. Okay, you can scale it up. Right now, we're going to use a value of 1 kilogram dry air as your basis. So I'm going to unshare this and we're going to use my iPad to solve this problem. You guys is going to help me solve it because I'm not going to, you guys, more or less, this is a revision. So you guys is going to tell me what the steps that we need to do in order to solve this problem. Yeah, I'm going to draw first our block diagram. Your basis, you need to write it down. It's going to 1 kilogram of dry air. 1 kilogram of dry air is going to be the inlet and the same value is going to be in the outlet. Yeah, so this is our block diagram. You have your 1 kilogram of dry, so not kilogram, sorry, I need to erase that. It's in English unit, it's not in kilogram. It's going to be 1 pound mass, 1 pound mass of dry air. That's the amount. That's one. Your temperature coming in is 80 degrees Fahrenheit. Your relative humidity is going to be 80%. And what else? We're going to cool it down to a value of 51 degrees Fahrenheit. That is the only information given except for the pressure. For both the inlet and the outlet, they are both at 1 atm. You're going to have water coming out, condensing. So that's going to be liquid water. That's going to be pound mass. We don't know the amount of water. Let's give it a value of this is going to be, we're going to use the same symbol as the textbook. So this is going to be M3. Okay, that's M3. Your outlet A is going to be noted as M2 of pound mass. I'm not going to write it there. I'm going to write it below here. M2 pound mass of water vapor in it. That is water vapor. So M1 is actually the pound mass of water vapor in the inlet A. Okay. M2 and M1 and M is not the amount of the total flow rate. We are just looking at the amount of water vapor in the inlet and outlet. They are not the total humid air. Right? And the M3 is the liquid water that condenses. So the next part of the question asks for what is the amount of heat that need to be removed. Heat. And that's going to be in between because we are dealing with English unit. So guys, even though the question asks for 1,000 feet cubic per minute, we're not going to write that down here in our diagram because we're going to have a basis of 1 pound mass of dry air only. So that same amount of 1 pound mass of dry air is going to be in your outlet. The same amount will be in the outlet. Okay, so what's the next step, guys? Before that, I need to show you guys the psychometric chart having the English unit. Where is that psychometric chart in the English unit? Find it. Okay, let me get the chart in English unit. Okay, this is the chart. I need to copy this so that it be in the same slide as our example. This chart is really, okay, there's a lot on it. So let's copy that and let's go to our example. So this is our example. I'm going to press it. I'm going to do it down because of overlapping here. Okay, that's it. Now tell me what to do, guys. What should be the step? The next step.
We need to find the absolute humidity as well as the specific volume from the.
Sorry, can you repeat that again?
We need to find the absolute humidity and as well as the for the inlet condition and as well as the specific volume.
Okay, for the inlet and the outlet condition, the absolute humidity, and what else do we need to find?
Specific volume.
Specific volume. The volume, the humid volume, you mean?
Yeah, humid volume. Sorry.
Okay, humid volume for both inlet and outlet. Okay, let's go about that. So humid, absolute humidity for the inlet condition. So the inlet condition is 80% and 80 degrees Fahrenheit. So let's zoom up. Where is 80%? That is 80%. Yeah. And where is our, I'm going to change that to red. Our 80 degrees Fahrenheit is somewhere here. That is 80 degrees Fahrenheit. So I'm going to, let's see, draw a straight line through that line, to that 80%. Sorry, 80 degrees C. 80 degrees Fahrenheit. I keep on using SI unit. I'm so used to SI unit. I need to get smaller so that I can draw a straight line right up to the 80%. Okay, is that a straight line? Not really a straight line, but okay. Doesn't look like a straight line, but better than nothing. That is your 80% relative humidity. So our point of interest will be here. It will be there. That is our point of interest. Okay, so if we go through horizontally, we get the absolute humidity. So let's look at the scale. This is a bit tricky. There's two scale over here. That is, I'll do that. That is gram of moisture. This is pound of moisture. So which one are we going to use?
The second one.
The second one.
Pound of moisture.
Okay, thank you. So we're going to draw a straight line horizontally from our inlet condition to the second scale. Okay, that's I should be getting a line on that on the straight line. It's not straight. I mean, it's not on that line. Is it on that line? It's somewhere in the middle. Eh, that's roughly, what is this for me? Interval 1, 2, 3, 4, 5. Okay. That's roughly 0.0182, roughly. That's all, write it as 0.0182. Not sure what your textbook gives the value. So let's see what the textbook has for that value. Oh, the textbook gives it a value of 0.018. We somehow managed to get 0.0182, no problem. So we stick with 0.0182. I'm going to change this to black color. So that is going to be 0.0182 pound mass of water vapor per kilogram. Okay, I need to erase this amount. Okay, I need to get that. Then I can write per kilogram of dry air. Okay, this is now is M3 mass of water.
Doctor, I
Yes.
think it should be per pound mass of dry air.
Pound mass of dry air.
Yeah,
Thank you very much. I seem to be so used to SI unit. I'm not used to English unit, so thank you. So now, since you already assume that you're going to have 1 pound mass of dry air, that is your basis. So the amount of water vapor in that stream is going to be 0.0182 because this is per kilogram of dry air. Your basis is one, well, so not kilogram, I keep on using kilogram. Because your basis is 1 pound mass of dry air and your absolute humidity, the unit is per pound mass of dry air. So that is the amount of M1. Yeah, the amount of M1 is going to be 0.0182. That is the amount of water vapor in your inlet air. So now let's look at sorry, somebody just left with it. Let's look at the outlet condition for the air. Your air condition is going to be at 51 degrees Fahrenheit. The outlet condition is at 51 degrees Fahrenheit. Where is 51? Let's get that using red ink. 51, that's 51. Then you go a straight line. That's 51. Okay. So did it mention anything about it being saturated or anything like that? Let me look at the question again. You're going to cool down to 51 degrees Fahrenheit.
yes, it's saturated. I think that.
It's going to be saturated.
Yes.
There's no mention of it being saturated. Somehow there's no mention of it, but we're going to assume because there's no way we're going to find the second location or the final location, the final condition, if we don't have it saturated, isn't it? Because we only have the temperature. With only the temperature with no relative humidity, then there's no way of getting the second position. So we're going to assume that it is saturated.
I think it's 100% relative humidity because the water has condensed.
Sorry, I can't hear you because somehow it's lagging or is it broken?
I said like the relative humidity might be 100% because the water has condensed.
Okay. The question says that you're going to have the water condenses, right? Okay, you got it. The water condenses. So that means it's going to be on the 100%. Right, that's right. Very right. You're very right there. Okay, thank you. So it condenses. So it has to be 100% on the 100% curve. So if we look at that position, it will be here. 50, that is 50, that's 50. And it's listed there is 50. So we're going to find the relative humidity by projecting it horizontally to the humidity scale. If I use that as the line, we getting a good line there. Okay, roughly, that's going to be 0.008. And that's your absolute humidity for the second position, 0.008. That's your final position. That's 0.08. So if you're going to write it down, you're going to write that using a black marker. So 0.008 pound mass of water vapor per pound mass of dry air. Again, we all know that we're going to have 1 pound mass of kilogram of dry air in the outlet. So the amount of water vapor in that outlet stream is going to be the same value, which is 0.008. That's the amount of water vapor. So now you already have your inlet air having the amount of water vapor in it, 0.018, and the amount of outlet air having a value of 0.008. So you should be able to do the material balance. Based on the material balance, be able to solve for the amount of water that condenses. Okay, so do the material balance, your water balance. Somebody tell me how to write it.
M1 equal to M2 plus M3.
M1 equals to M2 plus M3. Okay, we have the value of M1, M2, which is equal to 0.0008 plus M3. Oh, so P for M3, 0.0182 minus 0.008. So that will give you a value of, let me calculate, so that we can check what is the answer. After this, we can check the answer. Even in the textbook, obviously it's not going to be the same because we already know we got a different value just now for the absolute humidity. So this is going to be your pound mass of water that condenses. Right, guys, did you get the same value of ID? 0.0.
Yes, sir.
Same value, Doctor.
Same value. Thank you very much. The value in your textbook is 0.01. Okay, that's about the same. So now let's look at the next part of the question. The next part of the question asks for the amount of water, fraction of water that condenses. Okay, we already know the amount of water that condenses. We already have a value of 0.0102 pound mass of water that condenses. It asks for a fraction of the water that condenses. And how are you going to go about that? Anybody give me an idea?
Divided out by the total mass
Total mass of what?
of water,
Where? Which one?
the entering water.
Okay, so that value that condenses divided by total value that is in the inlet, the amount of water in the inlet, which is M1, or 0.0182 equals to, so if you multiply that, if you divide that by 0.0182, the total amount of water in the inlet, that will give you a fraction of 0.5644. Okay? That's what I got. Did you get the same value? Anybody getting a different value?
Yes,
You did? What value did you get?
same.
Okay, thank you. Okay, Ibrahim. So that's the fraction. It asks for a fraction. So that's the other part. It asks for the amount of heat that need to be removed for every 1,000 feet cubic per minute. But we're going to be our basis now is 1 pound mass. We do it based on 1 pound mass first. Oh, sorry, 1 pound mass of dry air first. Okay. So we need to find the enthalpy for the inlet and the outlet condition. Do you agree with that? Because we're going to do an energy balance in order to solve for the amount of heat that need to be removed. You think is that going to be the method, or somebody have a different method?
Yes, I think that's the method. Okay.
Okay, do the energy balance. Okay. Let's look at our graph here. Our enthalpy is the scale on the left hand side. And we have this enthalpy. If I highlight this, this is at the enthalpy at saturation. The unit is BTU per pound of dry air. That's the reason why your basis just now is per pound of dry air. You realize that so far, most of the unit is per pound of dry air. That is for your enthalpy. And the other thing is for your absolute humidity is also per pound of dry air. It could be pound, it could be kilogram. That's the unit. So right now, the reason why we choose our basis as per pound of dry air, because that makes it easier to calculate. Okay, so now that's your enthalpy at saturation. Where is the deviation? Let me highlight the deviation using a different color, using blue. So where is the deviation? Is there enthalpy deviation? I can see enthalpy deviation over here. That is your enthalpy deviation curve. Your enthalpy deviation curve is somewhere like here. That's the enthalpy deviation. Yeah, that's your enthalpy deviation. I will go up to here. After this, there's no more. Yeah. So for your inlet, where is your inlet? Your inlet is here. This is your inlet. Your inlet is at that point. And the enthalpy deviation, so if we project it, this enthalpy deviation stop there. Okay? Yeah, another enthalpy deviation stop there. So enthalpy deviation for minus 0.6 stop there. This also stop there. The next one will proceed right up to the top of the graph. But your location of interest for the inlet is there, and you have no other enthalpy deviation except for the one on the right, which is minus, what is that? Minus, what value is that? I cannot see the value. What is the value? Let me tell that, let me zoom out. That's 0. This is 0.3, 0.2, sorry. This is 0.3. This must be 0.2. This must be 0.1, minus 0.1. The minus 0.08 is somewhere there. So, since there's no other deviation on the left side of your point of interest, this is your point of interest. There is no other value on the right hand side. You only have one value on the left hand side. That value, if you write it down, that will be minus 0.1. Okay, based on this minus 0.3, that's minus 0.2. So that is minus 0.1 BTU. But the one on the left hand side, minus 0.08, is stopped there. So that means it is too small, the enthalpy deviation is too small for you to deduct it from the saturated enthalpy. So you can just get your value of enthalpy from the enthalpy scale without deducting the enthalpy deviation, because it stopped there. It doesn't reach up to the top. You can ignore the enthalpy deviation because it's too small. Okay, so now what we're going to do, we're going to project it. I'm going to use a red line, projecting it to the scale, the enthalpy scale. Make sure I get a straight line. Okay, that's roughly 39. That's about 39. But the unit is BTU per pound. That's 39 BTU per pound mass of dry air. I need to write that in black ink actually. Okay, so that's 39. So that is your inlet condition. The enthalpy of inlet condition. So we're going to erase this. So your enthalpy 1 is 39 BTU per pound mass of dry air. Okay, so we do the same thing for the outlet. The outlet air, so that's H2. Specific enthalpy, it has to be specific enthalpy because it's per pound mass of dry air. So for the outlet, where is our outlet condition? Our outlet condition is there at 51. So it's already, we know it's already saturated. So all we have to do is just project it on towards the enthalpy line. Okay, so that is about 22, 24, 26, 28. So 20.8. That's the value 20.8. So if I write that, that's value 20.8. Okay, 20.8. Not yet 21. So that's 20.8. So our enthalpy 2 is going to be 20.8 BTU per pound mass of dry air. What next, guys? Before that, somebody suggest something. I missed something.
Reference state.
Yes, thank you very much. And what is the reference state?
Based on the table psychometric chart condition.
Mhm. Yeah, I know, but the thing is, I can read it from this chart. Let's see, the one that I have over here. What is the reference state? Can you see? The reference state that it should be liquid water at 32 degrees Fahrenheit. The dry air should be at 0 degrees Fahrenheit, 1 atm. Yeah, it should be at 32 degrees Fahrenheit, 1 atm. So write down that as your reference state for that example just now. Yeah, water liquid at 32, dry air 0. So let's go back to our graph, to our example. 32, take note of it. So reference state, once you use the psychometric chart, you must follow the same reference state. Reference state or reference condition, it is liquid water. You can write like this, liquid water, 32 degrees Fahrenheit, 1 atm. And you have your dry air. How does it say this? Now, I know it's 0 degrees Fahrenheit and 1 atm, but let's have a look. Okay, 0 degrees Fahrenheit. 0 degrees Fahrenheit. You don't need to write gas because air is only in a gas form. There's no way air is going to be in a liquid form. So you don't need to specify the phase of dry air. Okay, so that's your reference state. Okay, next. What next? What's next, guys? You need to draw your table, isn't it? You need to construct your table. Yeah? You have 2 rows. Yeah, not very good at constructing my table over here. I have my A. I have my water. Liquid. Okay? Inlet. Mass. In. Out. In. Between. The mass. Dry A. You don't need to write the dry A because there's water there. Out. Mass. And then your enthalpy out. Between. The mass. Yeah. So that's your table. Your amount of A coming in is what? What should be to fill up that table? What is the amount of A coming in?
1 pound mass.
Okay, good. 1 pound mass because your unit of enthalpy is per unit pound mass. So that will be 1 pound mass of dry air. Same over here coming out. There's no water coming in, but there is water coming out. What is that mass of water coming out? Anybody? Any idea? What is the amount of water coming out?
It's the mass like 0.001.
You have too many zero there. It's 0.0. Oh yeah, right. Yeah.
0.0102.
Okay. So 0.0102. That's the pound mass. So now we already managed to get the enthalpy just now of the inlet air. We have 39 for the inlet air. For the outlet air, just now we got a value of 20.8. 20.8. So what do you think is the amount of the enthalpy for water, liquid water coming out? Anybody? And how to get it?
From saturation tables?
Saturated table, steam table, you mean?
Yes.
Okay, let me see whether I have my steam table over here, appendix. Okay. We need to look at English unit. Weighted steam, no, not the one. This is in SI unit. We have English unit, guys. I seem to be just looking at English SI unit. Okay, that's SI unit. No longer steam table. This is not steam table. You don't have. So what to do? Any idea? We don't have any steam table in English unit. Not here in this appendix, but we do have it in other references.
Convert the out condition to the SI unit and find it from the table.
Okay, that since you guys okay, I have a better suggestion rather than doing conversion. Okay, since your test or you are online, right? Why don't you search it using the English unit? Because definitely you'll be able to find it somewhere in English unit, isn't it?
Yes.
Okay, but my question next is the steam table, just now when you did the reference state, you mentioned that the reference state for the water is liquid. I'm going to highlight it at temperature of 32 and 180 N. You have to make sure that your steam table has the same reference state as that condition, or else you cannot use that steam table. Okay? If your reference state is not at that same condition, your other choice is to do integration using the polynomial equation, because you have a different reference state from the steam table, so you cannot use the steam table. You have to make sure that the steam table has the same reference state as your reference state. So I'm not sure whether I have that value here. Let me show you guys I'm trying to find my steam table in English unit. I do have it. Hold on. I do have it in I have appendix from Dean Copley's. You will be using this textbook, Dean Copley's, when you do your mass transfer, heat transfer. Let me try to get it for my, oh dear, where is my Dean Copley's reference? Hold on, let me find Dean Copley's. I'm going to use this textbook as your textbook when you're doing your heat transfer and separation. One, I'm still searching. Okay, I saw it just now. Okay, I'm going to unshare this. I'm going to look at our Dean Copley's appendix. I'm going to stop sharing this. I'm going to share you guys the Dean Copley's appendix. Let me see, where is that Dean Copley? Okay, hold on. Okay. Let me get this bigger so that you can see. Now, I'm going to share you guys the screen. Okay, did you manage to see that, guys? This is the appendix A to 9. That is in SI unit. That is in SI unit. This is in English unit. Can you see appendix A to 9 in English unit? Can you see, guys?
Yes, yes, yes.
Good. Okay. What is the reference state? Somebody give me a reference state for this steam table. Appendix A to 9.
32 Fahrenheit.
Okay.
Liquid.
Good. Liquid. Okay. The enthalpy is 0. You can follow my cursor. Okay. My enthalpy is 0 at liquid water, and the temperature at that enthalpy 0 is 32.02. So that is your reference state. 32.02 degrees Fahrenheit and liquid water. So that is your reference state. So that is the same as the reference state that we used just now for our psychometric chart. So we can use the value of the enthalpy from this steam table. Okay, now let's find the desired temperature. Our desired temperature, sorry?
Sir,
Yes.
we can also use the thermodynamics
Textbook.
steam table. Yeah.
Yes.
There
Yes.
is also English units.
Yes, good. So you can use that too. Okay. So right
That's
now, I'm not sure whether the thermodynamic value textbook gives you an exact value of 51 degrees Fahrenheit. because the one that I have over here is only 50 and 55. So that means I need to interpolate, okay, in order to get the enthalpy for the liquid water.
Doctor,
Mhm.
can we use heat of vaporization formulas that we studied earlier in this chapter?
Sorry, can we use what?
Heat of vaporization formulas, Watson correlation, and the other formulas.
Heat of evaporation formula
Is it relative?
to get the enthalpy. The enthalpy will be, you will use your hypothetical path, you mean.
Mm-hmm.
The problem is it's in English unit. You can use the in SI unit first. Okay, you do your hypothetical path. There's no problem using in SI unit first. Okay, and then change it to English unit. Use you can use it, no problem. Use the integration. Okay, use the value of A, B, C, D from the table in SI unit, and then convert it to English unit. No problem.
Okay, doctor, thank you.
Okay, so if you use the thermodynamic textbook, the appendix is there a value of 51 degrees Fahrenheit? Anybody? No?
I already interpolated. It's 19.31.
19.31. You already interpolate. Okay,
Yeah.
thank you very much. Thank you very
Good.
much. I'm going to write that down first before I forget. Your enthalpy for 3 is 19.31, is it?
Yeah, but like someone double check that should be.
Okay, Ibrahim said it's 19.31. Is the unit is BTU per pound mass? Somebody double check if you interpolate it from the appendix from the table A29. If you interpolate it between 50 and 55, sorry, that's the value. Between
Yes,
each-
correct. It's
Thank
correct.
you. Thank you very much. Thank you very much. Okay, now let's go back to our iPad. It's almost 10 o'clock. Let's finish this example. This is a typical example we have already looked at in SI unit, but unfortunately we have this example in this unit. So just do the same method, the same procedure, except that you'll be using the psychometric chart using the English unit. Okay, now we have everything here, 19.31. So write that down here, 19.31. So you have everything filled out. Write your energy balance. Your energy balance for this is an open system. So you have your pH, your change in enthalpy, your change in potential energy or kinetic energy first. Your change in potential energy is equal to Q, your heat, plus your work shaft. Okay, drop off your potential energy, kinetic energy, and work shaft. Reason, give reason. I'm not going to write it down. So you end up with having your final equation. Your heat that you need to calculate is going to be the change in enthalpy. That's going to be out mass times by its specific enthalpy in mass the specific enthalpy. So let's do the calculation based on the table. You have 1 times by 20.8. That's the value for your outlet A plus your water times by 19.31. Okay, that's the outlet water that condenses. So the amount that the inlet air, let me write out 1 times by 39. Okay, so that's the inlet air. So if you do that calculation, so what will be your answer? The answer, the unit will be in BTU because you already cancel off the pound mass. Somebody give me a value. Minus, it will be, sorry? 17?
Minus, minus 17.8.
Thank you. Thank you. So that's the minus 17.8 BTU. That corresponds to 1 pound mass of dry air. The question did not ask for a pound mass of dry air. the question, if you look at the question initially asked for 1,000 feet cubic of per minute, 1,000 feet cubic per minute of outlet A at the final condition. Okay. So change that into pound mass of dry A. How to go about that? Anybody? Any suggestion?
The volume divided by the specific.
Okay. Where are you going to get the volume from?
Specific from the chart.
From the chart. At what condition?
Outlet condition.
Outlet condition. Okay. So that is your outlet condition here. Okay. You have to spray it on the 100% saturation. So your volume is this. Sorry. Okay, that's I need to change the color. Let's use a green color. That is the stick line, diagonal line. That is your diagonal line. For that is 13 cubic feet. The others, the other diagonal line, the stick diagonal line is this line. Right? And this is 13.5. So where is our point? Our point is not really on the 13 cubic feet of volume. It's slightly more than that. So you need to do sort of an interpolation between these two lines. These two lines that I have highlighted in green. So let me get the line that is the parallel to this line. Let me use a different broken line. Okay, so let's do that. So this is our outlet condition. We need to get a straight line that is parallel to it. How parallel can I get? Okay, that's it. So how to calculate? Anybody? We have to do the interval again. Same thing that we did before. Okay, how many intervals do we have here? Oh, this is difficult, isn't it? We start from here. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, about 19.8. So it's about 19.8 intervals. That will give your distance of the difference of 13.5 minus 13. That is going to be 0.5 minutes. Sorry. Somebody get me one interval, please. Calculate for me one interval. One interval will be? What is one interval? What is one interval?
0.252.
0.252. Is it?
You divide 0.5 over 19.8.
Okay, let me do that. 13.5 minus 13 obviously becomes 0.5 divided by 19.8 intervals, we get 0.0. There's another 0 in front of it.
0.0.
Yeah, 0.02. That's one interval. So now we stop here. We stop there. So how many intervals do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We have 18 intervals. So what is the distance from 13.5? So 18 times 0.0252, that will give us a value of 0.4545. So your that value, that volume, that humid volume of the outlet A is about 13.5 minus 0.454. Why minus? Because I'm going towards the left side. Okay, that's why I'm deducting it from 13.5. I'm going towards the left side, so it should be lesser value. 13.5. Hold on. 13.5.
Doctor, I got 0.4536.
What happened?
4536. Instead of
45.
4545.
Okay, hold on. Okay, 0.45. No point. Undo that. Yeah. 0.4536, is it? Okay.
Yes, 4536.
Okay, now let's undo that too. 4536. So if you deduct that, 0.4536. Oops. Somebody calculate it, please. I just got an error here. I got 13.046, roughly 13 point, round it off, 0.5. There's no way you can get 3 decimal places. It's by view, actually. So I got 13.05. That's cubic, that's cubic feet per unit of pound mass, dry air. Yeah, so change that based on your value of 1,000 just now. Oh, yeah, it's almost 9 o'clock. 10 o'clock. So you have 1,000 divided by that in order to get the dry air, 13.05. Yeah, 1,000 feet cubic per minute divided by 13. But 13 point, what did we get this one? 13.05. 05 feet cubic of pound of mass dry air. Yes, okay. So that is your pound mass of dry air. I'm going to speed up. I'm not going to get the answer. I'm not going to calculate because it's almost 10 o'clock. So whatever answer you get there, that corresponds to the amount of dry air of the outlet. But the amount of dry air that just now we use our basis just now is 1 pound mass of dry air. For that amount of 1 pound mass of dry air, we calculate the Q. We got negative 17.8 BTU. That's the amount of Q, the amount of heat that is going to be removed. So if you have that amount of dry air, so what is your Q that is going to be removed?
We're gonna times the Q by the amount of dry air.
Okay, that's how you do it. Yeah, it will be a huge value. Why? Because that value that you get here is quite a big value. 1,000 divided by 13.05.
76.62.
Sorry? 36?
76.62.
Okay, so that is 76.62. So 1 pound mass give you of dry air give you a value of minus 17.8 BTU. So if you have 76.62 of dry air, pound mass of dry air, so what is the Q? So just do it, interpolate it, minus 17.8 BTU per 1 pound mass of dry air, and you have 76.62 pound mass of dry air. So you cancel that, you will get your final answer. So what is the final answer? 1363.8 BTU. Remember the minus sign. Yeah, per minute. Why is there per minute? Because that is per minute. This is per minute. Yeah, so that it will be per minute. So that is your final answer. Hey guys, I'm sorry I took too much of your time. It's 2 minutes to 10, and I know you have another class after this. So thank you very much for attending. So if you have any question regarding this example, it's from the textbook. Have a look at it. Okay guys, and tomorrow we'll have another class at 2 p.m. But I will not be looking anymore at psychometric chart. We will start looking at chapter 9. So if you have it, okay, good. Thank you very much for your attendance. Assalamualaikum warahmatullahi wabarakatuh.
Assalam.
Thank you, Doctor.
Welcome.
Doctor, one quick question.
Yes.
The heat exchanger, do we assume the Q is 0 between the system and surrounding?
It depends. Sorry. It's not depend. The heat exchanger is only between the heating fluid and the cold fluid. It has nothing to do with the surrounding air. So it's adiabatic.
Yeah, within the system itself.
Yes.
So we assume Q is 0.
Q is 0 if it's with the surrounding air. But Q is not 0 within the system.
Yeah.
Okay.
Thank you.
Most welcome. Okay. Any other question? Okay, it's already 10. Thank you very much. Assalamualaikum.